Can you now see my new technology thingy? It's just, I'm assuming anyway that you can see what I can see. Can you just see one big screen with
Yes.
section 7.4 written on it?
Uh-huh. I see 2 pieces of paper.
Right, so it took a little while to kick in for some of you? Right, let me put this up here. Okay, that's working well. Well, let's get started. What we're going to look at today is section 7.4, and tomorrow we're going to look at section 7.5. Section 7.4 is going to deal with what are called confidence intervals. And most of the time, our job is going to be to calculate a confidence interval, right? To find one. So let's give you a bit of background. The typical question has a story attached to it, where someone conducted a survey or a poll, and they asked a question, and the answer ends up being a percentage of people that they asked said yes. So the question, let's pretend we've got one. Let's suppose I went and asked 200 adults, do you own your own home, right? Either mortgage or otherwise. And out of that 200, 142 said yes. And so what we're trying to predict, and all a confidence interval does, is it predicts what we think the likely percentage is going to be for all adult Americans, or whatever the population happens to be. So in this case, if we take 142 and we divide it by 200, that ends up being 0.71. And we have a funny little notation for that. Do you remember seeing the notation p hat? That's how you say that out loud. Have you seen that notation before?
Yes, sir.
Right. So p hat is 71%, but most of the time we leave things for calculation purposes as decimals. That's fine. So based on my very small sample, I could make the prediction that approximately 71% of adults live in a home that they own. So here's the problem, and this is what confidence interval tries to solve. How good an approximation is that? And what do I mean by how good it is? I mean, how likely is it to be actually the right answer, or at least dead close to the right answer? For instance, the right answer might be 60%, maybe 75%. How do we quantify how good this estimate is? Well, we quantify it by creating what are called a confidence interval. So, for instance, there are 3 basic confidence intervals. One's called a 90% confidence interval. The other is called a 95% confidence interval. And the third one is called a 99% confidence interval. Confidence intervals tend to be at those fixed amounts. The textbook goes into some weird ones, which I'm going to totally ignore and never use. I think if you read the textbook, they talk about you could have an 80% confidence interval, some weird number like that. They are not standard. Nobody in statistics uses those. So these 3 they do use. Now, what do they tell us? Well, we don't know yet what this confidence interval is, but can you imagine there was a number here and a number here, and bang in the middle of that number is my 71%. A 90% confidence interval would give you a start and a finish number, and we would be able to say that we are 90% confident that the real answer, right, the entire population of America answer, is in that range. So doesn't that give you a little bit more confidence? There's another word for confidence interval. A little bit more surety that how good your estimate is. So let's hold on in that story and we'll come back to that. And let's pretend we asked another question, and I'll just create made up confidence intervals so I can continue this theory. Suppose we went and asked people, you know, whatever it is, 5,000 people, do you like eating pickles? And 28% of them said they like it. 28% of adults like eating pickles. A 90% confidence interval might be 0.24 to 0.32, which basically means, if you turn it into percentages, because that's the way my brain works, is that somewhere between 24% and 32% of Americans like pickles. So if we actually went and spent a fortune and asked every single one of you, somewhere in the region between here and here would be our correct answer, right? Now, it could be 25%, it might be 31%, but we're pretty sure it's in that range. Have you noticed that the 28 is bang in the middle of those two numbers? So what does the 90% tell us? Well, it tells us two things. First, this interval, there is a 90% chance that this interval has the real answer in it. Doesn't that also mean that there's a 10% chance that the real answer is not there? That the real answer could be 50% or the real answer could be 5%. When you create a confidence interval, you are telling people a range of values and how confident you are that the right answer is in that range. You're not saying any more than that. You're not saying it's guaranteed, right? 90% is not guaranteed, right? If I created a 95% confidence interval, it would look something like this. Well, if you compare these two, this confidence interval, I'm now 95% sure that the real answer is somewhere in the range 20 to 36%. Have you noticed that it's bigger than this one? And that makes sense, doesn't it? Why should it be bigger than this one?
More range, so you're more certain what it is.
Yeah. Now, the third one could be a 99% confidence interval, and it might be from 16% to 42%. Have you noticed that that one is even bigger as an interval?
Yeah. As the confidence interval's increasing, it's widening it's getting wider.
Right.
Like
Does that make sense that it would need to be wider for you to be 99% sure that you've picked an interval where the right answer lives? That, you know, if you think it visually, don't you have to have a big interval if you want to be really sure you've got the right answer? It is impossible, theoretically, to have a 100% confidence interval, one where you can guarantee that the right answer is in there. And the reason why you can't do that is that if you're picking a sample, you haven't asked everybody, right? Isn't there a chance that the people you didn't ask had a different idea about liking pickles, or whatever the question is? If you want to be silly about it, I guess there is 100% confidence interval. If I said that the right answer was somewhere between 0 and 100%, would you agree that I'm 100% confident that the answer is somewhere between 0 and 100%? Because everything is, right? Either everybody likes pickles or everybody in America hates pickles, right? That's the choices at the extreme ends. So far, so good?
Yeah, sure.
Right, so let's return now to our question that we started off on, right? This one here. We're going to create one of these confidence intervals from scratch. So We started with 2,000 people, 200 I should say. 142 of them said yes. I believe my question, I've forgotten what my question was. What was the pretend story for this?
Do you own your own home?
Okay, that's it, thank you. So right now it's what, 71%, which seems a bit on the large side. So the first thing you do is you test that you can create a confidence interval. Right, in other words, are you even allowed to do this process? Well, we ask 3 questions. And some of the homework starts with these 3 questions. The first one is your sample random and independent? Isn't that the same question they asked in a lot of the earlier sections, right? I asked 400 people, is it a very random sample? There's no connections between anybody? Good. The second check is it a large sample? And the test for that is that n times p hat has to be greater than 10 and n times 1 minus p hat, whoops, also has to be greater than 10. So if I went back to this story and I asked people, did you own your house? And only 3 of them said yes. Do you know the NP hat would be 6 and it would fail? It's not, the sample wasn't big enough, right, to get a good estimate, a good confidence interval. And then the third thing is the population large enough? Most of the time we just assume that that's a yes, because common sense, you would say, yeah, there's millions of people in America. I'm pretty sure that's a big population. Technically speaking, it should be your sample should be less than 10% of the population. Oops. Don't know if you can hear that, but the guy who's cutting my grass is making a noise. Now, you can phrase that lots of ways. Another way of phrasing that is that the population should be 10 times bigger than the sample. That's almost always going to be yes. Now, phase 2. If we call that A, let's do B. We know p hat at 0.71. There's a guy I'm now going to calculate called the standard error. Technically, it's the estimate of the standard error, but it's still a standard error. Can you remember the formula that was used to calculate SA?
Yes.
Hey, go for it.
It's P and then 1 minus P over N.
Right. Now, the only difference here is that I don't have a P.
Yeah, it's...
I have a P hat. But
P
that you gave me the correct formula, which is what I was looking for, which is why you will see a funny little baby estimate. You know, we can't tell you exactly what the standard error is, but that's going to be pretty close to it, right? So that will be the one that we will use. So far, so good?
Yes, sir.
Now, the cool part.
Computation.
There are 3 magic Z scores. 3 magic Z numbers. They're very often got little asterisks on them. These guys here. And these numbers, these are just numbers and they don't change. But if you're going to do a 90% confidence interval, you use this number. So it's kind of cryptic, but what it's saying is the Z score, the number you're going to use for a 90% confidence interval, it's going to be the number 1.645. And you just write that down, you keep it in a piece of paper handy so it's there when you need it. Now, if you want a 95% confidence interval, the magic number is 1.96. And if you want to find a 99% confidence interval, the magic number is going to be 2.58. Now, I need these guys so I can show you the full formula for calculating, let's do a 90% confidence interval. The formula for getting it is p hat plus or minus the magic z-score for 90% times, I'm just going to call that guy SE instead of SE estimate. Will you pretend I'm writing estimate every time I do it, because it gets a bit boring after you write it 4 times. So our 90% confidence interval is going to be 0.71 plus or minus 1.645 times the standard error. So it's going to be 0.71 plus or minus 1.645 times this guy. And I didn't give myself enough room, but I'm going to try and squeeze it in here. The standard error is p hat, 0.71, times 1 take away p hat, which is 0.29. And the whole thing is going to be divided by 200. So I'm going to stop sharing for a second, and I'm going to share my calculator to show you, well, once I have my calculator up and running, here we go. I'm now going to share my calculator. There we go. Right, you should be looking at the full calculator screen now. Agreed? Right, so I'm about to do that calculation that I had written down. So it's the square root of 0.71 multiplied by 0.29, all divided by 200. And the answer I've got is roughly 0.032 and some stuff. And so I'm going to use 3 decimal places. I think is pretty standard in the homework. So 0.032. Are you happy about how it's a pretty straightforward calculation to get this fella here that's called the standard error, right? It's p hat times 1 take away p hat, all divided by 200. So what we're going to do now is return back to my screen. And do you see we now have that little fella? And so I should be able to put that right in here. And then I just do a couple more lines, and this guy is finished. It's 0.71 plus or minus. I'll use just my normal calculator right now. So I'm typing in 1.645 times 0.032, and I get 0.053. So far, so good? We good?
Quick question.
Yes, sir.
Yes.
For the z-score of 0.9, 0.95, and 0.99, are those numbers going to always be the same? Like
Yes.
Okay, just want to make sure.
Yeah, so the numbers we're talking about are these ones here, right? So when you're being asked to get a 95% confidence interval, that is the number you're going to use, 1.96.
And then
So
you
what's going to
minus-
change is 1.96 is going to go there when you do a 95% confidence interval, right? 1.96 obviously there, and that means that this answer would have changed, right?
Yep.
Right. Now,
Thank you.
if you look at these two guys, and I guess this is what calculators are for, 0.71 take away 0.053. At one side, I get 0.657. And then if I add the two together, I get 0.71 add 0.053, and at the other side, I get 0.763. And that guy there, this is our 90% confidence interval. Now, right now it's decimals, which is why, is what the calculator, we had to do it. In most people's brains, proportions make more sense when you write them down, not as their decimal value, but as their percentage. So based on what I've just done right now, we could say that we are 90% confident that the real percentage of Americans who own or mortgage, have a mortgage on their house is somewhere between 65.7 and 76.3%. So do you see, we've now got a kind of idea of how good my estimate is. Now, there's a lot of variation, isn't there, between here and here? I mean, that's quite a big, it's over 10%, isn't it? And that's quite a big interval. The main reason it's so big is that my sample was quite small. Do you know if my sample was 200,000? What do you think would happen then if everything else remained the same, but the sample size was much bigger? It was 200,000 or 20,000, whatever. What do you think would happen to this interval?
It would get smaller.
It would. Because if you ask a lot of people something, shouldn't you be more comfortable, more confident that your answer is going to be more realistic to the population, right? If I asked 20 people something and I asked 20,000 people something, wouldn't you be much more confident about the results from the 20,000 people I asked that question to than just the 20, right? And that's why they have a step 2. Is your sample large enough? Because what they don't want is for people to go out and do little stupid surveys where they only ask 20 people something and then come back and say with all the confidence in the world, which they shouldn't, oh, somewhere, 90% of Americans are in favor of banishing dogs, whatever the weird question had been. And the reason they got such an extremely answer is, if you only ask 20 people, couldn't you really get quite unlucky in your responses? Couldn't you just pick 20 sociopaths by sheer bad luck, right? So are we cool with the process, how you actually create a 90, 95 or 99% confidence interval? Are we good?
Yeah.
Right, so I'm going to just go through another example, another question, only this time we'll make it about politics, because we're in that world and very often you get this. So let's suppose I have a guy, candidate, there we are, candidate A. And it's coming up to the elections. And before the elections are always doing polls, right? Who are you going to vote for? Are the Republicans going to win? Are the Democrats going to win? Is John Smith going to win? Is Peter Smith going to win? Those kind of questions. And you hear them say things like, we believe that candidate A is going to win. If the election was held tomorrow, candidate A would win. And you might wonder how they can come up with a prediction on something that hasn't even happened yet. Well, they're making lots of assumptions. One assumption is that the people who said, yes, I'm going to vote for him, actually go out and vote for him on the day of the election. And they may not turn up, right? And that's actually quite important in many elections. You may have a lot of people who support that political party, but they don't turn up and vote. And that's why you can get what they believe is weird results. Not weird results. And if you don't vote, you don't vote. That's why you never got your guy elected. So let's have candidate A. And we asked 1,020 people, because they always seem to ask weird numbers like that. And 570 said yes, they were going to vote for candidate A. And we are now going to create a confidence interval based on that data. And at the end, we're going to try and see if we can make a prediction about whether we think candidate A is going to win, you know, if the election was held tomorrow. So, we'll just talk through the steps. If you look at this, would you agree that there's no indication that it wasn't a random sample? So that's step one. Is it random and independent? Check. Is the sample large enough? I think 570 in that. If you do the NP hat, M1, it works. And basically, that guy there is NP hat. And who's left is N1 minus P hat. So you can tell just by scanning. And the population is really big. So we'll assume that that is good to go. So P hat is 570 over 1020. So 570 divided by 1020. And I'm looking at 0.559. Well, that's looking good for candidate A, isn't it? Majority of people are going to vote for him. In fact, to get elected, don't you just need 50% plus one more person? That's how you get elected, right? Half the vote plus one. That will get you elected in a two-horse race. Okay, the next one is just a choice. Well, let's do standard error, then we'll do the choice. Standard error estimate is the square root of P hat, 1 take away P hat over N. In this case, it's going to be 0.559, because that's P hat. Take that away from 1 and you get 0.4441. And the whole thing is going to be divided by N, which is 1020. So I'm doing this on my calculator. So I have a square root of 0.559 times 0.441. And I'm going to divide that by 1020. And I get the answer 0.016 to 3 decimal places, or 1.6%. We cool with that so far? Right, which one do you want me to get? A 90, a 95, or a 99%? Just make up a number, rather than me just keep picking one. You pick one.
95.
95, okay. So we are going to create a 95% confidence interval. So its formula is P hat plus the magic Z score for 95 times the standard error, right? In this case, P hat is 0.559. You'd have to have a really good memory, but maybe some of you have. Do you know what the magic number for a 95% confidence interval is? What's this weird Z?
1.96.
Well done. Multiplied by 0.016, which is standard error, and that becomes 0.559 plus or minus, let's see what that guy looks like, 1.96 times 0.016, and I get the answer to 3 decimal places, 0.031. Looking good? Now, that gives me, on one extreme, 0.82528, and at the other extreme, 0.59. In percentages, 52.8% up to 59%. So we're predicting with a 95% degree of confidence that if you asked everybody in that city, are you going to vote for candidate A? That the answer would be somewhere between, what, 52 and a bit up to 59.
Mm-hmm.
Now, you see, we've actually got something here. On the radio or the TV the next day or whenever they get round to it, they might say, the latest poll has candidate A in the lead, and we believe he is going to win that election. Now, when you look at this confidence interval, would you agree that every single one of those numbers is bigger than 50%?
Mm-hmm.
And that's why they can say, we believe candidate A is going to win the election.
Right.
If I did a different question, let's pretend the numbers just came out different. And let's pretend that the numbers were 49 to 58%, right? Just for argument's sake. If that had been the confidence interval that we created, you can't say that candidate A is going to win the election. What you would probably say instead is a phrase like, it's too close to call, or they're within the margin of error. You heard those phrases? Within the margin of error, or it was too close to call. And you're thinking, what are they talking about? Well, theoretically, isn't 49% just as valid as 58%, right? So couldn't the truth end up being that, yeah, candidate A only gets 49%? Now, we're imagining this as a two-horse race. So if one of them gets 49, doesn't that mean his opponent got the rest, 51%? So actually his opponent would have won. And confidence intervals don't put any specific weight on any number. Every single number in that range, from the first to the last, is just as likely to be the right answer as any other number. And one last little flaw. You see this little bubble here? If you put it together with this one, you sometimes get the answer written like this: 55.9% plus or minus 3.1%. Do you know this plus or minus guy, especially when it's written as a percentage, has a special name? It's actually made up of 3 words. It's called the margin of error. So if you've ever been on TV, and maybe now that you'll pay attention, and they talk about a poll, right? They've conducted a survey or a poll, and it doesn't need to be about politics. It could be about anything, you know, abortion, whatever it might be. They will quote to you what the margin of error was. So they'll say 42% of the people are in favor of this, and the margin of error was plus or minus 4%. If you think, you might not have noticed it, but maybe you'll start noticing it now. Do you see how that tells you a little bit more than just this number? Doesn't that give you a little indication of how much wiggle room or how accurate your estimate really is? That makes sense?
Yeah.
Right. Suppose I told you this story. The number of people who like pickles in America is 30%, with a margin of error of give or take 20%. Based on that information, would you agree that is a very weak predictor? Because couldn't the truth be anywhere in that huge range? On the other hand, if I told you a story and I said it was 12%, give or take 1% as a margin of error, do you see how close your interval is? So I might be 90% sure that the right answer is somewhere between 10 and 50, or I might be 90% sure that the answer is between 11 and 13. Do you see how the margin of error is a good reflection on how accurate a survey or poll you've conducted?
Yeah.
Right, I think we have time. Yeah, we got time for, well, is there anybody came across some homework questions they'd want me to do? Otherwise, I'm just going to do another example and take you through the process. Okay, so let's continue where we left off. Let me hold off for a few seconds here. I'm going to stop sharing. Right, I just want to make sure that no one was waiting to get in. Right. Okay, let's imagine we conducted another survey. And what will we do this time? I'm just making up stories, so I guess it doesn't matter. Somebody had a lot of time on their hand and they conducted a survey with a sample size of 20,000 people. And they went and asked them, and 1,312 of them said yes. Not a very big percentage, but never mind. 1,312 of these people went and said yes, they actually like watching soap operas on TV. So it's quite a small percentage. We would like to use this sample to create a 99% confidence interval on what we believe the percentage of Americans who like watching soap operas on TV is. So I'm going to make the assumption that we've done all the randomness and the large thing and jump right into the meat of the question. So that's our first guy, right? What percentage, or in this case, what ratio did we get? So 1312 divided by 20,000. And the answer you get here is 0.066. I'm sticking to 3 decimal places here. Now, the standard error of the estimate is the square root of p hat, 1 take away p hat over n. It's the square root of 0.066 times 0.934 divided by 20,000. I haven't done it yet, I expect that to be a very small number. Why can I make that prediction without even going near my calculator? What about the information in front of you kind of suggests that it's going to be a very small standard error? You notice n is huge. If you divide a number with a really big number like 20,000, don't you tend to get a really small answer? So that's why I can make this prediction. Let's find out how small it truly is. The square root of 0.066 multiplied by 0.934 divided by 20,000.
0.00.
Yeah, 0.002, I guess. Oh, God, that is tiny, isn't it? Now, let's do a 99% confidence interval. So I'm going to be, when I'm finished here, I'm going to be 99% confident that my interval, right, has the real answer to the population, all of Americans who watch TV. It's going to tell you what percentage of them like watching soap operas. So for a 99%, it's p hat plus or minus the magic number for 99 times your standard error. So it's going to be 0.066 plus or minus, anybody know what that guy is?
2.58.
Yeah. Now this doesn't matter, but I'm going to tell you anyway, because you may look up other books and, you know, see a difference. This number here is sometimes called 2.578. So you might look up a textbook or do something online, and this guy here might be 2.78, 2.578. It's the same thing if you round it off, but I'm just saying that just in case you get a little bit unsure. So that's going to be 0.066, give or take. Well, actually, I've got this guy, got this real estate. Let's use it. if you go 2.58 multiplied by 0.002, you get, give or take, 0.005. Now, as an interval, we'll do that in a minute, but if I call that 6.6%, give or take 0.5%, the margin of error in this case is 0.5%. Now, if you get a margin of error of only 0.5%, do you know that that means there's not going to be much wiggle room? Our interval is going to be quite tight, which is good news. Right, back to the decimal version of this. If you add 0.005, you get 0.071. And if you subtract it, you get 0.061. And I believe in a lot of the homework questions, you're expected to put in the decimal version. Me personally, the way my brain works is, we are 99% sure, right, that that interval contains the real answer to what percentage of all Americans like watching soap operas. It's roughly, you know, between 6 and 7, right? Now you see how tight that interval is, how close they are to each other, and how large my confidence is on that being a good predictor of where the real answer is. Have you seen the power that this gives you then? It allows you to come up with not asking everybody in America anything, but just asking a small group, but using that to predict an interval on which you can be pretty sure, in this case 99% sure, that the true answer is inside. That's very, very powerful. And it's very, very common. If you watch the news any time within any given day, it'd be almost impossible for you not to miss one story where somebody conducted a poll or a survey on something. And this is the method in which they can do it. That means you could actually, with a little bit of time and effort, do the same thing. I'm going to move this guy. Are we good?
Sir.
No questions about that? Do you feel comfortable now about how you're going to be doing a lot of these questions?
Yes.
Right. So why don't I change tack and do something a little bit different? And I'm going to go, and hopefully I've got this set up. I'm going to go inside and see if we can look at a homework question. Can I do that? Mate. Are you looking at my lab statistics page?
Yes.
Right, so this one here should be on, is this 7.4 or 7.5? This is 7.4, right? So let me pick a question at random. This is question 10, and I'm going to open that up. Okay, so can you actually see question 10 on the screen yet?
No.
Okay, I thought that might happen. So won't take me more than a few seconds. What I have to do is I have to go back out and then back in. It's just the idiosyncrasies of sharing. Oh, wrong one. Darn it. Let's try that again. The writing is so small and my eyesight's so poor that I thought I'd clicked on the right one. I'll pay more attention this time, see if I can see it. Here it is, gotcha. There, are you looking at the question 10 that I'm looking at?
Yeah.
Right, okay. This question says a survey of adults in a certain country found that 68% believe that protecting the rights of those with unpopular views is a very important component of a strong economy, a strong democracy. I'm rather disappointed that it's 68%, but well, I guess that's not a very nice country. Now, assume that the sample size was 700. We're going to go through a set of questions, which are for many of them are going to be just the same as what we've done. But you know, they like to put in extra little bits. So let's talk about each of the extra little bits as they happen. So how many people in the sample felt that way? Well, do you know this 68% that they've just given us? Do you know that's p hat?
Yeah.
Right.
Yes.
And you notice that over here that we've got 700 people in the sample. So although you might not be able to see me do this, what I'm going to do now is I'm going to find, yeah, and we'll assume that it is, and it's 476. So 476 people out of 700.
So, sir, what you did is you convert it to decimal and then multiply it to 700, right?
Exactly. So
Okay.
although they give you percentages, you almost always use decimals in any of the calculations, including this one.
Okay.
So if you notice that when I did standard error, it would be decimals I would use, right? And when I do confidence intervals, all the working is decimals. Percentages really don't come in until you've got an answer and you want to write it in a way that makes more sense to human beings. And I think most human beings like percentages better. So I'll check my answer and I better say great, or fantastic even. Now, is the sample size large enough? Well, remember the rule for sample size large enough is n p hat is bigger than 10 and n1 minus p hat is bigger than 10. I don't need to do a calculation. Would you agree that from a sample of 700, 476 of them, that's a decent size, right?
Yeah.
It just needs to be bigger than 10. So it's one of the yeses. Yes, the sample size is large enough since the estimated standard error, nothing to do with standard error. Yes, the sample size is large enough since the expected number of successes is and the expected number of both of which are greater than 10. So in this case, I'd be putting my 476.
And then the difference.
And I guess I should be able to do the other one in my head. Shouldn't I just take that away from 700 and that's what's left? So what's that, 224?
Yeah.
Right. And both of which are greater than or equal to, check. So do you see that they're getting you to do the 1, 2, 3 at the beginning, but not phrasing it that way? They're actually getting you to kind of do a calculation along with it. And of course it is. Now it says find the 95% confidence interval. So what have I got here? I have a 68%. So I have a p hat 68, and I have a sample size of 700, and we are looking at is it 95? Yeah, 95. Okay, so I'm now going to leave that and go back to our usual sharing, and we'll see what that looks like in a moment. Now, I think this is the third or fourth one. It's probably the fourth one that we've done. So we should be getting pretty good at just the format because they don't really change much. Are you all happy about that being 1.96?
Yes.
Right, you take the little list and you stick it in a piece of paper and you keep it handy for this section. And the little list is the Z for 90, 95, and 99. So ready for a 95% confidence interval. P hat plus or minus the magic Z score for 95% times the standard error of the estimate. And I forgot to do that, so let's find it out. It's going to be p hat, 1 minus p hat, all over n. I'll just do that in my calculator. So what have we got? I got a square root. I can put it here. I got a square root of, that doesn't help. Let's see, 0.68 times 0.32, all divided by 700 people. And I'm looking at 0.017. I'm getting deja vu here. Oh, it's 0.18, isn't it? Can you see? Yeah.
0.8.
Yeah. Easy mistake. Now, that could have made my answer just a tiny bit wrong. And you know how unforgiving the software is? So you did it all right apart from a bad rounding off, and you're wondering what went wrong. So that guy goes there, that guy goes there, and this guy goes here. And so I'm now going to get the margin of error, which is 1.96 times 0.018. And that's 0.68 plus 0.035, which gives me 0.68. Take away that decimal, which is 0.645, and then 0.68, add that decimal. So let's do a check on that. So we believe that the confidence interval is 0.645, comma, up to 0.715. And unless I screwed up, oh, nice work. Okay, here's a new question. Find its width. I haven't talked about its width. What do you think they mean by that? How wide something is, its width. Last chance. Anybody got an idea?
What's the question, sir? Again, sorry.
Yes. They ask you in this next question to find the width. And I'm saying, what is the width of this particular confidence interval?
Oh, you have to subtract the, I can't see the screen.
Oh,
Sherry.
you can't see it? Oh, sorry, that doesn't help. I thought I'd done the out and in thing correctly, but evidently I haven't.
No, I can see it now.
Okay, right. If you take the difference between,
So,
if I just put
yeah.
your words into, take that away from that, it ends up being that the answer is, according to my calculator, 0.07. So from the biggest to the smallest, right?
Yeah.
And that then is going to be check answer. I think that is good. Now assume the sample size was 2000. Unfortunately, I don't have any more time. I've just got another class that's about to start. But if you went back and did the question, but changed the n to 2800 and you went through the whole thing again, you would get a totally different answer.
Yeah.
But it's going to be, compared to that 700, that 2800 is what, 4 times bigger? So don't be surprised if the answer to the interval is actually smaller, because more people, more accurate answer. Okay, everyone, I'm going to have to say a very quick bye-bye. So hopefully I've covered enough for you to get that section done. And I'll see you tomorrow when we look at the last one, which are basically confidence intervals on the difference between two populations, proportions. Okay, bye-bye, guys.
Bye. Thank you, sir.
You're welcome. Okay, bye-bye.